Now here we have another interesting phenomena. With the help of that we can find out period of oscillation. We know whenever a ship gets tilted along the longitudinal axis, now because of the shifting, a couple of magnitude W weight multiplied by gm is metacentric height, sin theta, this couple starts acting to bring it back to original position. Now this couple is equal to what? Couple is equal to I alpha, where I is the mass moment of inertia, Im. This Im is different than what we have just studied I. That I was the second moment of area about the longitudinal axis, and this Im is different. This Im is mass moment of inertia of ship along the longitudinal axis. We have to keep this thing in mind. This Im multiplied by alpha. What is alpha? Alpha is angular acceleration. So angular acceleration may be written as d2 theta divided by dt square. And why we have minus sign here? Minus sign is because this couple tries to oppose the acceleration, right? It tries to oppose the acceleration, that is why we have a minus sign. So this equation may be, which is T is equal to I alpha, very famous equation. So this may be rewritten for small theta d2 theta divided by dt square plus wgm divided by Im theta is equal to 0. This is a famous equation. If we solve this equation, we can find out the time period of oscillation. So time period, or the time of a complete oscillation from one side to the other side and back again, time period, which is very known term, time period is equal to 2 pi root of Im divided by Wgm. If we solve this equation, we can find out the time period for this equation, or time period of ship along the longitudinal axis. So time period is equal to 2 pi root of Im divided by Wgm. So if Gm goes up, what happens to time period? Time period will reduce. Time period reduce means now it will take less time to complete the fluctuation. In this formula, we are not considering the force offered by the fluid, because this ship is inside the fluid, means portion of the ship is inside the fluid. Wherever this ship wall is in contact with the fluid, now that whenever there will be relative motion between the ship wall and the fluid, this will offer a viscous resistance. So viscous resistance is not being considered here in this formula for calculating the time period. So because of the viscous resistance, this time period will be, this fluctuation gets died out till new wave comes, but right now we are not considering that force being offered at the surface due to the fluid. So this time period is equal to 2 pi root of Im divided by Wgm. If Gm goes up, time period reduces, it means frequency goes up. So if ship is fluctuating very rapidly, it means that these passengers, if it is carrying passengers, those passengers feel uncomfortable, right? So and what is Gm? Gm is the metacentric height. So if Gm is high, we know that ship is more stable. Though ship is more stable, but it will lead to uncomfort of the pupil. So in case of ocean going vessel, this Gm is generally kept between 0.3 meter to 1.2 meter. Now if Gm is increased, then it is better for stability, but period of the rolling reduces. Because of that, the comfortable of the passenger is less. Comfortable for the passenger, comfort level reduces. But if Gm goes up, then stability is high, right? So generally we keep the metacentric height for ocean going vessel at 0.3 to 1.2. So if we have a passenger ship nowadays we have very few passenger ships, we have more cargo vessels, so we keep metacentric height closer to 0.3. For vessel, cargo vessel, we try to keep it near 1.2 meter to have more stability, right. And in case of warships or racing yachts, the stability is most important, so in that case also the metacentric height is kept more. So it means that if we increase the metacentric height, we reduce the comfort level of the human being moving in those ships. So we have to keep this thing in mind, and we have to compromise between the stability and comfort depending on our design criteria. Now we shall discuss about fluid and rigid body motion. Now if we have a fluid in any container and that container is moving, then how to analyze this type of situation, because in practical life we may have to supply gasoline through containers moving with the help of train or moving with the help of trucks. Similarly, we have to supply liquid like milk or another crude oils with the help of ships and train. So if a container is filled, suppose if it is filled up to half height or 3/4 height, and that container accelerates, in that case what happens, that fluid rushes towards back. When fluid rushes towards back, then how to analyze this kind of situation when a container is subjected to acceleration. When container is subjected to acceleration, though initially the liquid fluid surface gets tilted, but for that acceleration that liquid fluid surface remain constant, right. So with reference to the container, fluid is in static equilibrium condition, because fluid does not move for that acceleration barring the initial disturbance. So with reference to the body, this fluid is in static equilibrium condition, and everywhere wherever this fluid is in contact with the solid surface, a perpendicular force is applied, because we know that whenever there is a tangential force, the fluid can't resist tangential force, it will start moving. So when a fluid moves under acceleration in a closed container, this may be treated as a rigid body motion. When we can treat it as a rigid body motion, we can apply the corresponding equation, force is equal to mass into acceleration, and we can find out how does pressure vary in x direction, y direction, z direction, and we can solve such kind of problems like if container is open, what type of acceleration it can withstand without splashing the liquid outside the container, or what happens to the pressure on the top of the container if it is accelerating at different values, right. So these type of questions can be answered with the analysis which we are going to do.